Hey everyone, this is Chapter 11 Review. In this video, we're going to go over density, pressure, buoyant force, and Archimedes' principle. First, density. It's defined as mass per volume. The SI unit for density is kilograms per meters cubed. We're going to deal with density with water as our fluid for a lot of problems, so we should know its density is 1,000 kilograms per meters cubed. It's also useful to know that the conversion to grams per centimeters cubed is 1. That's a very useful conversion to know so that you don't have to spend your time converting between the two units. In this picture, we can see that the bread is squished, and so its volume is getting smaller, and you know that when volume gets smaller, the density is going to be greater. You know that squished bread is more dense than the regular bread. Let's do another example. A brick is cut in half. What happens to its density? Keep in mind that this is not the same thing that happened over here. If a brick is cut in half, its density is not going to change, because if you think about the density of the brick is mass per volume. And if you look at the density of one of the pieces of the brick, the piece is going to have half the mass, but it's also going to have half of the volume. So the factors of 1/2 cancel out. Each piece of brick still has the same density as before. So make sure to look and see what variable is changing, mass or volume or both, to see how the density of an object is affected. Next is pressure. It's defined as force per area. The SI unit is Pascal. Let's look at an example. Why can a balloon be popped with a needle but not a finger? Usually it's really hard to pop a balloon with a finger. And that's because a finger has a lot more area than a needle. So when you're applying a force to this balloon over here, if we look at our equation, pressure is force per area. If you have a big area for a finger, that is going to exert way less pressure than a needle, which has a much smaller area. How about how pressure varies with depth? This is the equation over here. P2 equals P1 plus rho GH. P2 is the pressure at the bottom of the liquid. P1 is the pressure at the top of the liquid. Sometimes the top of the liquid is open to the atmosphere. In this case, the pressure at the top is equal to P0, which is equal to 1.01 times 10 to the 5th pascals. And then rho GH stands for the pressure due to the weight of the fluid. Rho is the density of the liquid, and then G is acceleration due to gravity, 9.8 meters per second squared, and H is the height of the liquid. Let's look at a question. How do the pressures at points 1 and 2 compare? We can see that both pressures are at the same depth. One is under an iceberg and one is not. Since both points are at the same depth, those 2 points are going to have the same pressure. This is due to this equation right here. The pressure at this depth just depends on the depth below the surface. You may think, well, what about the fact that there's an iceberg here? Well, both points still have exactly the same amount of weight above them, and so they're going to be at the same pressure. Also, if they weren't at the same pressure, let's say we had more pressure over here, then that means that the liquid would flow from the high pressure to the low pressure. But we know that everything is staying still here. We're in equilibrium, so the points must be at the same pressure. So an important takeaway here is that all points at the same depth, as long as they're in the same liquid, must be at the same pressure. Next is Pascal's principle. It tells us that pressure is transmitted equally to all parts of a fluid. You're usually going to use this principle when you have a hydraulic system, such as you can see in this picture here. You have an enclosed fluid, you have pressure applied at one end where there's maybe a smaller piston, and then you have pressure at the other end, which is going to be the same. Because we have a bigger piston on one side, we're going to have a greater force on that side. And this is due to applying the principle which says F1 over A1, which is the force at the small piston and the small area, is equal to F2 over A2, where F2 is the force at the large piston and A2 is the large area. Let's look at an example. A hydraulic lift produces 240 times the input force. How much larger is the output cylinder than the input cylinder? According to Pascal's principle, if you have 240 times the force, so if F2 is 240 times F1, then that means that the area 2 over here is going to have to be 240 times area 1. If both of these are 240 times F1 and A1, then when you plug them into Pascal's principle, we can do that. We have F1 over A1 on the left. On the right side, we're going to plug in the answers, 240 F1 for F2 and 240 A1 for A2. And that's the only way that the ratios are equal to each other. So however much bigger is the force, that's however much bigger the area is going to be. Next up is buoyant force and apparent weight. Objects appear to weigh less when submerged, so that means that their apparent weight is less than the actual weight. So let's look at this example, which just tells us that we need to derive the equation for the apparent weight of a submerged object. The first thing you want to be able to do is draw the free body diagram for the submerged object. Our object is going to have a weight pulling it straight down. It's going to have a buoyant force straight up. The buoyant force acting on objects that cause the object to appear to weigh less, is always an upward force. And then we can see that there's a string, so there's a tension upward and away from the object. This tension is actually going to be equivalent to the scale reading, so it will be the apparent weight. Now we want to set up Newton's second law. We know that the object is in equilibrium, so the sum of all the forces in a y direction is equal to 0. Calling B and T positive because they're going up, we're going to add them. Then we're going to subtract the weight since it's going down. That's going to equal 0. If we are solving for the apparent weight, which is T, then we're going to get T is equal to W minus B. And this shows us that the apparent weight, when submerged, is less than the actual weight because we can see that it's weight minus the buoyant force. How do we calculate buoyant force? We're going to use Archimedes' principle. Archimedes' principle says that the buoyant force equals the weight of the displaced fluid. In equation form, we have buoyant force is equal to density of the fluid times V, the volume of the fluid displaced, times G, which is our 9.8 meters per second squared. So if we take a look at this picture here, we can see that the object, once it's placed in water, it appears to weigh less, like we just talked about. What we also see here is that the object is displacing some liquid when it's put in. So the amount of liquid that is displaced, that volume, that is what V fluid is. That volume of the fluid displaced is equal to the volume of whatever part of the object is underwater. So when the object is completely submerged, that's the entire volume of the object. If the object is floating and only partially submerged, then it's whatever part is underwater. And what we can see is that the buoyant force is equal to the weight of this displaced fluid. So this expression here stands for the weight of whatever this amount of liquid is. So that's this weight here. That means this weight here, that's the buoyant force. Let's look at an example. Which ball experiences the greatest buoyant force? Assuming both balls are the same size, we have one that sank to the bottom and one that's floating. You may think that the one is floating is experiencing more buoyant force. However, according to this equation, if they're both in the same liquid, that means the density of the fluid is the same. G is the same for both. What matters most here is the volume of the fluid displaced. How much liquid is each object pushing out of the way? The floating object is only pushing this much liquid out of the way, while the one that sank to the bottom is pushing the whole volume of the entire object. So this object at the bottom has more fluid displaced. That means that it has a greater buoyant force than the object that is floating. And finally, how do we know if an object is going to rise or sink? If an object is going to rise, then that means that the weight of the object is going to be less than the buoyant force, as we can see in this picture here. If the buoyant force is greater than the weight, then it's going to accelerate upward. There's a net upward force. Also, when an object rises, that means that the density of the object is less than that of the liquid. The opposite happens when the object sinks. The weight of the object is greater than the buoyant force, and the density of the object is greater than the density of the liquid. Let's look at an example. An object has a density of 3.4 grams per centimeters cubed. Does it sink or float in water? We want to compare the density of the object to the density of water. The density of water, if we keep it in grams per centimeters cubed, we said earlier, was going to be 1 gram per centimeters cubed. So we can see that the density of the object is greater than that of water. We have this case over here, which means that the object is going to sink in the water. So when you're comparing densities, make sure that both densities have the same unit. And now finally, for a floating object, what do we know? We know that the buoyant force equals the weight. They balance each other out. This actually gives us this special equation that is valid when you have one floating object. The volume of the fluid displaced divided by the volume of the object is equal to the density of the object divided by the density of the fluid. What's important to know about this equation is that this ratio here, it stands for the fraction of the object that is submerged. Fraction of object submerged. And that's because if you really think about what it means, the volume of the fluid displaced is whatever volume is underwater. If you divide that volume by the entire volume of the object, then that's the fraction of the object that is submerged. So that's useful when you have this type of example. A floating block is 2/3 submerged in water. Find its density. So if it's 2/3 submerged, that's the fraction of the object that's submerged. That's equal to this ratio here. So that means that the density of the object divided by the density of the fluid is equal to 2/3. So all you have to do to find the density of the object is multiply both sides by the density of the fluid. And we know that the density of water is 1,000 kilograms per meters cubed. So we're going to get 667 kilograms per meter cubed. That's going to be the density of the object. So the object was 2/3 submerged, and it was 2/3 as dense as the water. And that's it for our Chapter 11 review video.